Okay, part 2, section 4.7, optimization. The farmer has 2,400 foot of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? All right, so I read the problem. I think I understand what's going on. We got a river. The farmer wants to put a fence along the river. Rectangular field like this. It's a straight river. He needs no fence along the river. There's 2,400 feet of fencing, and we want the largest area. Okay. Because it's rectangular, whatever this side is, I'm going to call it X, is going to be that side. And this side over here, I don't know, so I'll call it Y. And I know that then the area of that region is going to be X times Y, or more correctly, I should say that the area function has two independent variables. So A of X, Y is equal to X times Y, and my goal is to maximize that area function. But I can't. I can't maximize a two-variable function because my knowledge of calculus is limited to one-variable functions. So now what I need to do is find a way to get a secondary equation, some other piece of information here that I can use, to do a substitution to turn two variables into one variable. And I think that that is going to be hidden in this. Okay? That we're going to use 2,400 feet of fencing to make this happen. And since we're going to use 2,400 feet of fencing, I know that 2,400 needs to be equal to 2x plus y. That this length plus this length plus this length better add up to 2,400 feet, or 2x's plus a y is 2,400. Now I'm going to use that to do a substitution. The most obvious way would be to say solve this thing for y and say that y is equal to 2,400 minus 2x, and then do a substitution right there. And then we're going to get the area function A is equal to x times 2,400 minus 2x, or if you prefer, 2,400 x minus 2x squared. Okay? Now, it would make sense to say this. It would also make sense to say this, that our numbers need to be between 0 and 1,200. 0 because negative numbers don't make sense for x because we can't have negative length. And where did 1,200 come from? Well, it came from right here. Because if x gets bigger than 1,200, what happens to y? Y goes negative. So I know that the only place that I'm looking for answers is on the interval 0 to 1,200. All right. Now that I've got all of the first part of this done, in terms of what's going on here, I am now down to this. So let's just take a look at what we wrote here. We identified all the given quantities and made our picture. That was the x's and y's in the picture. We wrote a primary equation. That was our area equation. But we recognized that it had a issue, that it has two variables, and we can only have one variable. So we wrote a secondary equation, and that was that if you want to think of it as perimeter, it's kind of like perimeter. It isn't really perimeter because perimeter implies all the way around. And we didn't go all the way around. We just went three sides of this, but kind of like perimeter. Okay? And we did substitution. Then we determined a feasible domain of that primary, okay, 0 to 1,200, and now we're down to calculus. So I need critical numbers. So what's A prime? Well, A prime is 2,400 minus 2x. I'm sorry, 4x. Oops, almost made a mistake there. I took a derivative. And if that's A prime, then what are our critical numbers? Well, I don't think there's any of the does not exist type. Because I can't think of a single number that I could put in for x here that would make that equation not exist. But I can't think of a f prime, or I'm sorry, in this case, A prime equals the 0 value. That would be 600. 4 times 600, 2,400, 2,400 minus 2,400, 0. So I know that I have one critical number. So now I'll test. I'm limited to 0 to 1,200 and one critical number at 600. That gives me two intervals to test. I'll pick interval number 1 first, and I'll use 1 because I'm lazy and that's easy. That's going to give me positive, which means we are increasing on that interval. Our area is increasing between 0 and 600 for x. Now I'll pick a number over here. I'm going to use 700. Plug that in there. 4 times 700 is 2800. 2400 minus 2800 is negative, which means you are decreasing. So what does that make this? A maximum. So area is maximized when x equals 600. And what's y when x equals 600? Well, that's where I go back to this right here, my substitution statement. 2 times 600 is 1200. 2400 minus 1200 is 1200. So that means that y is 1200. Now, it would be inaccurate for me to say that the answer is x is 600 and y is 1200, because if you go back to the original problem, and I'm going to erase what I wrote here. If you go back to the original problem, anywhere in that problem do you see a definition for x or a definition for y? And since those definitions are not in the problem, I can't use those variables in the answer. So I need to write the answer up so that it makes sense. Right? And I will say that the area is maximized when the region is 600 feet. Let's see. I'm going to say perpendicular to the river and 1,200 feet parallel to the river. All right, I optimized area. That wasn't too bad. It only took 7 minutes. Let's see if we can do it again. A rectangular page is to contain 24 square inches of print. So you must be a printer now. Right? The margins at the top and the bottom are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? Okay. I'm going to have to draw a picture to see if I can even understand this. So I have a piece of paper. It's a rectangle. And there's print in the middle. Okay. That print needs to be 24 square inches. The margins at the top and the bottom are 1.5, so this is 1.5. This is also 1.5. And on the left and the right are 1 and 1. So this must be like a rectangle within a rectangle, so to speak. Okay. And then I want to find the dimensions of the page. So the least amount of paper is used. So least amount of paper, that means we're going to minimize something. Okay. So I need to find the dimensions of the page so that the least amount of paper is used. Okay. So I'm just going to call this x and this y and see what happens. Right. So the function that I want to minimize is the area of the page. Area of the page is going to be x times y, or more correctly, area as a function of two independent variables is xy. I can't minimize this. My job is to minimize. I can't minimize this because it contains two variables. So I'm going to have to go back in and try to find some sort of secondary equation so I can do a substitution and minimize a single variable function. So if we have two variables, we need one variable. We need another variable reduction equation. And I think the piece of information we haven't used is this, 24 square inches of print. But that's that inside piece. And I don't know the dimensions of that inside piece. So how far is it from there to there? Or how far is it from here to here? Right? I think horizontally, that's x minus 2. Whole width is x. An inch in and an inch in on both sides will give me x minus 2. Similarly, vertically, I think that's going to be y minus 3. So then my secondary equation, the one that I'm going to use for substitution, is going to be the equation horizontal times vertical is equal to 24. And now I need to do a substitution on using that equation over here to make that equation less ugly. Make it go from 2 variables down to 1 variable. This is going to be ugly to solve for x or for y. It's not going to give us something nice. If I solve that thing for y, if I do the math and I solve that thing for y, I first of all am going to get y minus 3 is equal to 24 divided by x minus 2. And then y is equal to 24 divided by x minus 2 plus 3. And then this is what we'd have to use for our substitution, which is really going to be a hot mess, because we're going to have to take a derivative of that. So I'm wondering if maybe we should rethink how we define our variables. Because we chose these. We can unchoose them and make them easier. Okay? Wouldn't it be better? Wouldn't it be easier if this was just x times y equals 24? So let's do that. So what I'm going to do is I'm going to get rid of all of this, and I'm going to start over. And I'm going to say that these dimensions here are not x and y, but that these dimensions on the inside are x and y, which makes those outside dimensions x plus 2 and y plus 3. So then our area function is going to be x plus 2 times y plus 3. And our substitution, our secondary equation that we're going to use to do our substitution is just x times y equals 24, which makes it a lot easier to work with. I like this. I like this a lot. I'm going to solve this for y. So y is 24 divided by x. I'm going to do a substitution right here on that variable. And then I'm going to get then that overall area as a function of only x is going to be x plus 2 times 24 divided by x plus 3. And then I'll FOIL that out. First times first is going to give me 24. Outer is going to give me a 3x. Inner is going to give me a 48 over x. And last is going to give me a 6. I can combine the 24 and the 6 and just make that be 30. Okay, so now I have area as a function of only x is 30 plus 3x plus 48 over x. There's my function now that I need to optimize. Okay. Are there any restrictions upon x? Well, it'd be safe to say that x can't be negative. And there probably is some upper limit what x could be before this rectangle would get so wide that it would be silly in terms of its height. But I'm not going to worry about that. I'm just going to say there's no reason, mathematical reason, for x to get too big that would make y turn negative or anything like that. Because in here, there's nothing in the math that's going to say it could get too big. So I'll just use infinity. All right. What do we need? What do we need? What do we need? Oh, we're to the calculus part. So we need a derivative. A prime. A prime of x is going to be 3 minus 48 over x squared, which gives me critical numbers at 0 from the doesn't exist side of things. But yeah, obviously 0 sucks because that would mean that we didn't have any printed area. And okay. What about the equal to 0 part? When is 3 minus 48 over x squared equal to 0? Well, that's when 3x squared is equal to 48. Move the 3 over, multiply by x squared. So x squared is equal to 48 divided by 3, which is 16. So x is equal to plus or minus 4, but we're going to ignore the negative and say that we only need the positive 4. Okay, So now I'm to the point where I'm going to test intervals. Hard stop at 0, no stop on the big end. 4 is the only number I really care about. Again, this is 0, technically a critical number, but not one that I'm worried about. I'm going to test 1. When I put 1 into that derivative, 1 squared is 1, 48 divided by 1 is 48, 3 minus 48 is negative. So we are a decreasing function. Now I'm going to test 4. Or I'm sorry, to the right of 4, I'll use 5. 5 into there, 5 squared is 25. 48 divided by 25, 48 divided by 25 is less than 2, right? 3 minus less than 2 is going to be positive. So we are increasing. Oh, what just happened there? That was weird. Program just crashed. Hopefully it saved it. It saved it. So we will be increasing. So what does that mean about this guy? Well, that was a critical number where it was equal to 0, so horizontal tangent line, so decreasing, increasing, horizontal tangent minimum. So we found our minimum. Now here's where we have to be careful though. They want the dimensions of the page, and we found that x is 3. But what did we call x? Remember, when we set this thing up the second time, this is what we made x. So how wide is the paper actually? It's x plus 2. And then how tall is the paper? Well, y plus 3, but I don't even know what y is yet. So if x is 3, what's y? Where was our substitution? Oh yeah, it's right there. Y is going to be 24 divided by 3, and 24 divided by 3 is what, 8? Right? So what are the dimensions of the page? Okay, well our width is x plus 2, so we have a 5-inch width. And our height is y plus 3, so a plus 3, and an 11-inch height. And those are the dimensions of the page. Well, that's not too bad. 17 minutes. I still have one more problem to do. I will make it its own video because it's kind of a long one. So I'll see you all back here for part 3.